So, here we have Anna from Carbon 5. You might remember her from last year if you were here. She was so good, we decided we had to ask her back. What else? One of the foremost evangelists for Elixir, running Elixir Bridge, among other things. Great curriculum there. And if you don't recognize her, you might recognize her voice because she's also one of the co-hosts of Elixir Outlaw. So give her a round of applause, everybody. You need a microphone.
I'm going to need that. Thanks, everyone. How's it going so far? Wait, do a little bit better than that. Come on, how's it going so far? All right. So yeah, thanks, Brett. My name is Anna. I am a developer at a consultancy called Carbon 5. We build custom software for all kinds of companies, everything from super early stage startups through enterprise. And we're like a full service agency. We have product design and development in-house. We actually have an office in this building, one in San Francisco, New York, and Santa Monica. If anybody's curious, come talk to me. I think there's some other Carbon 5ers in the audience, so you could find them. That's not what I'm talking about today, though. What I'm talking about is looking at Go versus Elixir, and specifically looking at the concurrency paradigms of both languages. So I've actually given a longer version of this talk with my coworker, Hannah, and the inspiration for this talk really came from conversations we were having with each other and other people when we were talking about applications and dealing with concurrency. And oftentimes people would throw out Go and Elixir in talking in those conversations, but they're not the same, right? As with everything, we know that everything has trade-offs. And really when we're talking about comparing the concurrency paradigms in Go and Elixir, we're really talking about the actor model. We're talking about Erlang and Elixir. The actor model, and when talking about Go, we're talking about this thing called CSP, or communicating sequential processes. But before we actually kind of dive in and look at both and what's the same and what's different, I kind of want to take a step back and think about how we might define concurrency. And before that, where did this all really start, right? We know that in the beginning, computers didn't really have operating systems, right? You had one, they were designed to run like one program from beginning to end, and the program had access to all of the machine's resources. Thankfully, over time, that's changed, right? On multiprocessor systems, multiple processes can be executed in parallel. And I feel like, at least once a week, my fan starts burning on my machine. Probably every day, I have all these things running. I'm like, also, why are all of these things running? But how is this possible? And interesting thing is it's not really, right? We fake it. We know that like at any given instant in time, if you have a machine with a single CPU, only one process can be running in that instance, right? But the executable code for several processes can be loaded into memory, and the processor essentially switches rapidly between jobs to give the illusion that things are running in parallel. And at the risk of kind of oversimplifying, we know that a process can really only have one of three states, right? It's running, right? The CPU is executing statements in that process. It is ready, so it's loaded into memory but not yet running, or it is blocked. Another thing we want to set the stage for is that we also have these things called threads, right? And the only thing you want to keep in mind about them is that they're subsets of a process and they share memory. So how is this all relevant, right? Why do we care and why are we starting here? Well, we now have these more robust machines and we can do more with them, right? So how do we leverage that in our applications? So this brings me back to how we want to think about and how we talk about concurrency. I did not come up with this analogy. I stole it from somebody, or I'm borrowing from somebody who's much smarter than me on the internet, but I liked it, so I wanted to share it with you. So let's imagine you had 5 people. They all went to IKEA. They like the same bed. They each buy that bed. They bring it home, and they build it. And then at some point later in the future, you have like 5 beds. Now think about what the instruction set for building those beds would look like. To me, it seems pretty straightforward, right? They would each get the same set of instructions. Okay, well, what if you had 5 people, and they all went to IKEA and they bought 1 bed? Then they came home and started building it together. What does the instruction set look like so that each person can make progress on their task without actually blocking anybody else? And then at some point in the future, you have a fully functioning bed. So I don't know about you, but to me that sounds a lot more complex. So when we're talking about concurrency, right, can define it as the composition of independently executing processes, while parallelism is the simultaneous execution of computations. Now, if that sounds like a lot of words, right, which it kind of does, what we're really saying is parallelism is about executing many things at once. Its focus is execution. Concurrency is about dealing with many things at once. Its focus is structure. And that requires coordination. And this is really where we introduce complexity. So how do we really coordinate between these tasks working together? So I'm going to shift gears a little bit and talk about how we've traditionally dealt with concurrency, right? How do we organize work between multiple potentially parallel tasks that are working together? We have these processors that can get more done. So how do we take advantage of that? Well, and we know that the problem with having no coordination and just relying on parallelism is it actually doesn't get things done faster. Is anybody familiar with this image? Okay. So we talk about concurrency, we talk about keeping things unblocked, right? Moving faster, potentially in parallel. And as we see here, right, this NCIS image, 2 sets of hands typing on a keyboard actually doesn't type faster, right? Even though we want it to. So how do we coordinate? Well, the original solution is to use this concept of threads, right? Threads are these built-in concepts in operating systems. They're independently executing subsets of processes. And they share memory, right? And because they share memory, they actually share data. So the strategy that's traditionally been used, right, is to communicate by mutating these shared data sets. And a metaphor I like to think of is, let's say you have like a painting hanging in a room, and you have 2 people working on that painting. One person comes in, does some work, and then leaves. Another person comes in, sees the work that a person has done, does some more work, and then leaves. The other person comes back, right? They never actually directly communicate with each other. They only see kind of the changes that the other person has made. The problem with this is that it's actually really easy to override each other's work, right? So to prevent that, right, we introduce these kinds of locking mechanisms that we see in a lot of these traditional programming languages, right, like mutexes or semaphores, so we can serialize access to that data. And threads really are the original basis for writing concurrent programs. Because they're already built into operating systems, you kind of get this communication through shared data for free. Aside from like using a couple locking mechanisms. And this is why a majority of traditional programming languages support threads, right? They provide the basic mechanisms for communicating with this data. But as you can imagine, initially, right, it sounds easy and it sounds simple and we can coordinate all this work and it's awesome. But very quickly, it becomes problematic, right? We very quickly run into some challenges. One, we're dealing with lots of this shared mutable state. And I think I'm at the right conference where like I don't have to convince people that like having to constantly deal with large amounts of shared mutable state is like not a good idea. And because of that, right, if we're dealing with that, then we have to rely on the programmer to remember to like lock access to serialize this, to lock access to this data so they can do some work and then remember to unlock it. But what happens if they forget, right? And anybody else that's trying to access this program can't, right? Because then the program is locked. And so not only do you have like unpredictable problems with like managing the expectations of programmers, like remembering to do the right thing, but as you introduce more threads, right, and introduce more state, the complexity increases exponentially rather than linearly. So as we start digging into like Go and Elixir, we see these models, right, and the models, the concurrency models that they're leveraging as approaches to try and deal with these problems in a different way. So first, we're going to talk about the actor model. It's probably very familiar for a lot of you who are familiar with Elixir and or Erlang. How many of you are new to Elixir and Erlang? Cool. That's awesome. So for those of you, this will hopefully be helpful. For a lot of you, this might be a review. It's going to set the stage for the conversation that we're going to have in relation to Go. So the actor model. Fun fact, invented by Carl Hewitt in 1973. Erlang was created in 1986. And I read this, and I think it's true, but tell me if I'm wrong. But supposedly, the creators of Erlang did not actually know about the actor model when they wrote Erlang, which I think really speaks to the promise of the design pattern. So when we talk about the actor model, we're talking about this conceptual model to deal with concurrent computation. We're defining some general rules for how the system's components should behave and interact with each other. So this is an example of what it might look like, right? And what is going on here? Each of these circles has a mailbox and a little box that says internal state. Each of these units is called an actor, or in an Elixir Erlang land, a process, right? These are not operating system processes, super lightweight. They communicate by sending messages to each other. And they never share memory, right? Which means they never directly share data. So each of these processes maintains an internal state that can't be directly accessed by another process. And I kind of like this analogy when we're talking about the actor model. One ant is no ant. One ant cannot survive alone. Same idea for actors, they come in systems, right? In this model, everything is an actor. And each actor, or in our case, process, has a unique ID so that they can communicate with each other. And they communicate by sending messages, right? Or imagine like sending an email. And if we take a closer look at the sending of messages, right? We mentioned that each process has a unique ID. The messages are sent asynchronously, and they're stored in the mailbox. And when a process receives a message, it can do one of three things, right? It can spin up more processes, it can send a message, or it can update its internal state based on the message it's received, and that state will then be acted upon by the next message it receives. So the thing we want to remember about processes, or things we want to keep in mind, at least for the context of this talk, they're not operating system processes. They're lightweight, they do not share memory, and they have a unique ID. And when we were putting together this talk, the interesting thing that came to mind, especially in the context kind of Erlang, is in this case, the actor model is physically based. And what do I mean by that? Who still has a landline? Anybody? Does anybody still use their landline? I love it. And when was the last time you had a call dropped? Do you remember? Like never? Exactly, right? So the interesting thing when we were thinking about this is that in this case, right, this was built, right, this language was built to model the real world constraints of physical systems over long distances. So when we think about the functionality that we can leverage in this Elixir or Erlang ecosystem, it was necessitated by these problems that these language creators are trying to solve. Right? An example of this being like distributed Elixir. And I'm going to qualify this a little bit, right? Because things are inherently more complicated at scale. And the tools that we have at our disposal in this ecosystem do not at all solve any of the problems that are presented by distributed systems. But they give us they make it a little bit easier to get started, right? For example, each process has a unique ID. So a process can communicate directly with another process, whether it's on the same node or on a node halfway around the world. And given that a node can go down at any time, we would not want the sending of a message or the receiving of a message to be blocking in any way, right? So it's interesting to think that the messages are also kind of not time-bound in any sense. And we've all heard this phrase within this community, right? Like, let it crash. We are allowing ourselves to essentially build in this Elixir Erlang ecosystem these kind of self-healing systems, right? We have processes that watch other processes. And this goes back to the thing I was talking about with regards to coordination, right? We're building these self-healing systems that are allowing us to better coordinate our work. So if something goes down, the work still keeps moving forward. And theoretically, we build systems that don't die, right? We try to. But none of this runs in isolation, right? These processes don't run in a vacuum. We know that they run on the beam or the virtual machine. And the one point we really want to take away, at least for the context of this talk, is this idea of preemptive scheduling, right? We have this scheduler that essentially coordinates all of these processes and all these work. And it can interrupt a task, right, and allow another task to run without any permission from that running process. Again, another kind of pattern that allows us to take advantage of this coordination, allowing us to run our applications more efficiently. And if we think about like the priorities of the language, it kind of helps us understand some of the choices that have been made. We should probably say Elixir and Erlang priorities, not just Elixir, but the fact that they needed it to be scalable, right? Taking on lots of load. The fact that we had these systems distributed over long distances, so they needed to be fault tolerant and fast. So let's switch gears for a minute and now take a look at the other language we've been talking about, so Go and CSP. So, as I mentioned, Go's concurrency model is based on this thing called communicating sequential processes. It's a description for coordinating work amongst independent processes. And it was first coined by this guy, Tony Hoare, in 1978. Apparently the 70s were a really good decade for distributed systems papers. So again, in the context of CSP, a process just refers to like the smallest independent unit of work, essentially something that has a start and an end. And so in this context, kind of like to think about it as a sprinter, someone who has a defined start, runs for as long as they can, and then stops. And similar, as we talked about the actor model, right? Most implementations of CSP implement the version of a process on top of the operating system. So these are not operating system processes. So how do we coordinate work amongst these types of processes, right? Well, we're gonna go on with this like sprinter analogy, and imagine we have a relay race. Sprinter is running, and they have the baton, and they hand it off to the next person. The next sprinter waits until they actually get the baton, until they take off. So the baton, in our case, is called a channel. And it's the basic mechanism through which processes communicate and tell the process to start doing its work. So one important kind of difference from the traditional relay race is processes actually don't know about each other in CSP. They only know about channels. So you can imagine the sprinter hands off the baton, but they actually have no idea who they are handing off the baton to. They just hand off to the first person who's there. Not only that, but handing off the baton, the passing of it is actually synchronous. So imagine that I'm running in this relay race and I have a baton and I get to the end and there's nobody there, I'm stuck. I have to wait until someone's there to actually take the baton off my hands, right? So if I write something to a channel, I have to wait for somebody to read it before I can move on and do something else. So the last concept that's kind of essential to the CSP model that we're talking about is the idea of choice. So we're now approaching a pretty theoretical relay race, but stay with me. So imagine you're running and you're waiting for a baton, right? But you have a runner that's coming with a gold baton, and you have a runner that's coming with a silver baton, and you have no idea which baton you're gonna get, but depending on the baton, you're gonna go in a completely different direction. And if they both come at the same time, you're kind of gonna pick one at random. Okay, let's abandon our relay race. We're going to take a look at how CSP actually works in practice, using Go as our implementation. So, any Go programmers? Some people know Go. I know carbon fibers are in the room, so they know Go. Anyway, don't worry if you don't know Go. So just suspend your disbelief. We're just going to look at a simple kind of Go program. And our goal really is just to launch two processes. We're going to have one write to the channel. We're going to have one read from the channel. They're both going to notify their parent that they're done, so they can terminate. So this is our read function. So it takes a channel that's going to read from a string. So notice that the channels are typed, and it's going to notify its parent when it's done. And then don't worry about that like empty struct thing. We don't really need to transmit any data. We just want to say something happened, which is why we are using that. And here's our write function, which you can see is just going to write to the channel and then notify a parent that it's done. And here is our main function. So Go is actually a pretty low-level language, so we actually need to initialize our channels by telling Go to allocate them. But it is garbage collected, so we don't need to worry about cleaning them back up. So we're going to kick off the read and write in parallel. So the CSP equivalent in Go of processes are called Go routines. And the way you make something a Go routine is by putting Go, the word Go, in front of the function. Why are you laughing, Keithley? And so we're going to kick off both of them in parallel. We're going to put the read function before the write function to prove that they're happening in parallel, and then wait for both of them to be done. We actually don't need to wait for both of them to terminate, but then we wouldn't be able to guarantee that this print line that says finished would be the last thing to happen. So again, I think I've already said this, but every read and write to a channel is synchronous, right? If you write to a channel, it will block until somebody else reads. And the interesting thing about this, or the results of this, as you start to see in the example, is that you have pretty fine-grained control over the work being done. And so you can use the channels to have pretty predictable behavior if that's what you're after. So let's take a look at how Go actually implements CSP. If you look at the documentation, right, and dig into how Go defines Go routines, they say a Go routine is a lightweight thread managed by the Go runtime. Anybody think it's funny that they reference the word thread? We're talking about processes. It's not a mistake, because Go routines share memory. And they have access to the same data. So that's a little weird, right? But there's more. there's a library in Go called sync. And what you get with sync is like all of the basic locking mechanisms that you would get with any other threaded programming language. So you end up with kind of this like choose your own adventure with Go, where you could use the more regimented CSP-based model for coordinating work, or you could just use a mutex. And the docs, unfortunately, aren't as clear as you want them to be, because the docs initially say, don't communicate by sharing memory. Share memory by communicating. Except in the very next line, they're kind of like, well, but if it's hard and it's not going to work and it's going to be more confusing, then just use a mutex. One more fun fact, and a thing that's important to know that is in contrast to what we talked about when we were talking about the actor model and the Erlang VM, is that Go routines are scheduled cooperatively. So what that means is your Go routine basically has to hit certain statements while it's running in order for Go to interrupt and allow another Go routine to run. So if you create a Go routine that actually doesn't do any of that, you can essentially end up with this really confusing locking behavior. So some of you might be thinking like, WTF, what's going on? Seems a little weird. But before we like get all judgy, some of you are already judgy, I know, but before we get all judgy, let's look at a few other aspects of Go's implementation that like might help us get a fuller picture of like why the decisions that were made. So a couple things to know about Go. It compiles down to actual machine code. The Go runtime is like really small. A hello world executable in Go is about 2 megabytes, which is about twice as large as the C program. And underlying all of this is it's really trying to be a systems programming language. It's garbage collected, right? So you wouldn't really want to write an operating system in Go. But it's really designed to be a replacement for a lot of the other things you would like to do, maybe like native app programming. But it also wants to be flexible, which is why you kind of get this like kitchen sink of choose your own adventure the way you want to do things. Because it also wants you to be able to write a web server if you want to. And I think this is made clear when we talk about kind of the priorities of Go, right? It seems like the first priority is ease of adoption, right? Especially for C programmers. Like you can learn the basic syntax and concepts pretty quickly. It's a pretty flexible language. There's not a ton of convention, right? It doesn't have a lot of the higher level concurrency primitives that you see in Erlang and Elixir, right? There are no gen servers or supervisors. And it has concepts that'll be really familiar to folks that are familiar with threaded programming. 2 is that it's fast, right? It's supposed to be a replacement for C. And lastly, it's designed to be flexible in a number of use cases, right? So hence the choose your adventure approach, whether you want to write a command line program or you want to write a web server. So we've kind of talked a little bit about each of these models, but what's really different? Or are they more the same than they are different? And when would you use either? First of all, I think it needs to be said that they're far more similar than they are different, especially when compared against like traditional threaded programming. So both Go and Elixir manage their own concurrent code. They both have an abstract concept of executing a piece of code separate from the operating system, right? This means that you don't need to spend a whole lot of time worrying about scheduling pieces of code to run or worry about the memory management of having spun up thousands of Elixir processes or Go routines. And while Go is like certainly less rigid in its implementation of this than we see in Elixir and Erlang, they both emphasize message passing, sharing data by communicating as like the basic primitive for synchronization. And I think in this room, a lot of us would agree that maybe message passing is better. And there's no coincidence, right? Joe Armstrong himself has said that even though the actor model is its own theoretical concept, right, Erlang was heavily influenced by CSP. So what are the differences, right? One of the key differences is identity, right? We talked about how in Elixir and Erlang land with the process model, they have unique identities. In CSP, processes are largely anonymous. Once you create a Go routine, there's no way to really directly refer to it. And this kind of explains the communication patterns that we see, right? Because CSP processes are anonymous and they have no identity, they need a way to be able to communicate, and this happens through an intermediary, right? This thing that we're referring to as channels. So there's this layer of like indirection that we don't necessarily see in the Elixir or Erlang land. which also explains this kind of asynchronous versus synchronous message passing. And this might be one of the most important things, right, is that CSP messages are synchronous. So as soon as you send a message, you have to wait for somebody else to read it, which really kind of changes how you work with the language, right? You really wouldn't want synchronous message passing over a network necessarily. But are they really that different? This is maybe pushing it, not pushing it too much, but like you could give CSP processes an identity, right? If you have one channel and one process reading from that channel kind of becomes the de facto identity. And can we fake asynchronous message passing? Or not fake it, but actually implement it? This probably would not work for a distributed system, but if you were doing it locally, right? You can kind of have this message queue process where you'll have a channel on which you can send messages, and that process will just read all those messages and put them into some kind of buffer. Then you have another channel that's going to receive the messages, and anyone receiving on that channel will just get those messages when they come out. Asynchronous message passing. It's actually not quite that simple, but this is kind of like the canonical blog post for doing this in Go. There are a couple more steps, but it's really good. So if you're interested, I encourage you to take a look at it. So we talked a little bit about Go, talked a little bit about Elixir, their design paradigms, kind of what the advantages and disadvantages of both of them are. And the interesting thought that I was thinking about when I was kind of redoing this talk for this particular conference is this, and I promise this is not a tangent. There's a point to this story, so bear with me. But a couple of weeks ago, I was rock climbing with a friend of mine in Yosemite Valley. We were doing this like multi-pitch trad climb, and it's the kind where you like put in the gear, then you clip in your rope, and we get to the top. We brought 2 ropes. We're going to tie them together to rappel. Any climbers in the room? Right. So like rappelling is the most dangerous part of climbing because you're so dependent upon the rope and the anchors. And my friend John's been climbing a lot longer than I have, like 20 years. And he was like, you can tie this one type of knot, which we normally do for rappelling, or you can tie this other knot. And I didn't know that that was maybe not the correct knot to tie. Anyway, we tied this other knot. You leave a little bit of tail just in case the knot rolls so it doesn't come apart. And we're like 500 feet up. And the heavier person generally goes first, so he started rappelling. He gets about 15 feet down, and luckily I'm watching, but the knot starts rolling, right? And there's like about this much tail left, and I'm like, John, stop. And luckily there's a ledge he could stand on, so we pulled up the knot, retied it into the other one, which is the one that you're actually supposed to use for rappelling. And then we're both here, so it ended up fine. My point with that story, and it's not to be dramatic, right? But the point is like really understanding why the decisions were made for a particular thing, like, and when to use that thing, can really save you a lot of pain further down the road in situations, especially when they might be unexpected. So understanding like the design decisions initially can be hugely helpful. And that's all I got. Thanks for listening.